Hello everyone, welcome back. So in this video we are going to understand another problem of this contest for 58. The question is minimize maximum component cost. The question is saying that you are given an undirected graph and we have n nodes we have given, that is from 0 to n minus 1. Can we say that? Means from 0 to n minus 1. Then we have given 2D arrays like edges we have given, where edges at I means the one edge will be there where each edge contains two nodes u and v, and there we have a weight we have also given, right? Means it is saying that you are given a connected undirected graph with n nodes we have given, and each having a weight like this we have given, like wi, right? And it is undirected graph, right? Let me saying, then it is saying we also have given a k. So this integer k is equal to we can say the maximum number of connected components you are allowed to split the graph into, right? And so it is saying you are allowed to remove any number of edges, right? What is saying? You are allowed to remove any number of edges from the graph. So the resulting graph should have what? Should have at least k connected components. Means the integer that k we have given is equal to the maximum number of connected components you are allowed to split the graph. Can we say that? So what is our goal? So it is saying return the minimum possible value of the maximum cost among all the components after such removals, right? But there is a condition saying that means first of all understand what we need to do, right? Means we have to do what? We can remove any edges and we can split into at most k component. Now each component is nothing but a subgraph and has its cost equal to the maximum is weight. Maximum is weight in that component, inside that component, right? And we must need to find the minimum possible values of the maximum component cost after removal, right? After such removals. Can we say that? So let's understand that we have given n equal to 5, right? And edges is we have given like this, right? And kv equal to 2 we have given. Means this means there are 5 nodes we have. These nodes are like, give me 1 second. Means let's suppose this n we have given is 5. It means there are 5 nodes, right? These nodes can be what? Let's suppose 0, 1, 2, 3, 4. Can we say that? Because n is equal to what? 5. Number of nodes is 5. So these are the you can say nodes we have if we'll represent from 0 to n minus 1. So this is 0 and this is n minus 1. Means n is 5. So we can say this is 4, right? So index become 4. That we have given. There are 4 edges we have given also, right? Between this. So if we'll represent, let's suppose call as you can see here, right? So this is, let's suppose 0. This is 1. So from 0 to 1, we have weight is 4 we have given. See, this is 0, this is 1, and weight is 4 we have given. Can we say that? So this is given, right? Let me clean it so you will understand clearly. Okay. So very first, what it is saying, we have given our node, right? So this is the first at index 0. Okay. So we have given 0 and there is another node. So this is your u and this is your v. And between that we have 4 is a weight we have given. So this is representing like this. Can we say that? Now understand the next one, right? So next we have given is 1 to 3. So if we'll represent this, right? If we'll represent this u and v, so it will become like this. What? So one we already have. We need to write another one. Give me 1 second. As we have given, like that we will do. Okay. Then we have given what? Sorry. After this we have given node 2, right? And between that we have given weight is 3, right? Then what we have given 1 3 we have given. So from 1 and 3 we will take another node, right? Between that we have given 2. Then we have given 3 4, means from 3 to 4 will take another node, and between that we have weight is 6. So this is the thing we have given here, right? Now it is saying that k equal to 2 means you are allowed to break the graph into at most 2 component. Can we say that? means maximum we can remove means at most k connected components. In that we have to split it, or you can say remove it, right? But let's suppose we will split it, right? Means you are allowed to break the graph into at most two components because k is equal to 2. Can we say that? So what does the cost of component mean? Because see, we are also saying that the cost of component is defined as the maximum edge weight in that component. So if the component has no edge, its cost is 0. Are you understanding? Give me 1 second. Yeah. So this is saying, means if we will understand, so what is the cost of component mean here? What is the cost of component, right? Means a component is a group of connected components. Let's suppose I'll take a group of component like this, okay, and another group is, let's suppose we'll say this 4 itself. Can we say that? So there is two components that I will consider just for understanding. Understand, this is the component 1 C1 and this is component C2. Can we say that? So a component, as you can say, C1 and C2 is a group of connected components. So right, so itself is also a component, right? If you remove it, so if we say C1 contains how many? 1, 2, 3 and 4 component, 4 nodes we have, and so we can say 4 node connects itself, and we can say this is a connected nodes, right? And these connected nodes is a group of connected nodes. So this group of connected nodes is nothing but a component, right? And its cost is the, let's suppose what is the cost, right? So its cost is the largest weight among its edge. What is the largest among this? So this is the largest among this one. Can we say that? So let's suppose, just for understanding, right? For example, if a component has weight, let's suppose 2 and 3, right? We'll say 2 and 3. Can we say? So the 2 have 3 and 2, let's suppose we have cost, right? Let's suppose component will take here 2 and 3. Can we say that? So what is the cost is between this? So the cost is between 2 and 3 is 3, will say. The cost is 3. Can we say that? If a component has a weight, let's suppose 2 and 3, so the cost will become what? 3, right? So if a component has weights, let's suppose 2 and 3, if we consider this one, right? So what will happen? It will become 2 and 3. So this time we'll considering this component. If we'll take the whole component, right, means we have to we have to check the components, right, that has the weight, right? So so now we can say that this is the thing we have to understand, right? Okay, give me 1 second, guys. So what I am saying that if we have weights 2 and 3, right, if a component has is with weight 2 and 3, so we can say the cost is what? 3. Can we say that? So if a component has no is, let's suppose no is, means cost is, this is saying 0. If there is no weight is there, means itself, let's suppose for now, let's suppose this is the component itself, for one component is there, means only one node we have, right? In that case we'll say it is 0. So you have to understand what is the cost is there, right? We have to understand. So what we do, we are allowed to remove some edges, right? We can remove some of the edges. Let's suppose I will break this edges, right? So this will become independent one, C2, and this becomes C1, right? Means we can do what? We are allowed to remove some edges so that we can end up with at most 2 components. So our goal is to make sure that the component with the highest cost is the smallest as possible. Understand? What is our goal? Our goal is to make sure that the component with the highest cost is the smallest as possible. I hope you understand, right? So give me 1 second. Okay, so now understand. So let's suppose I hope you understand, right? Now understand, build the how we are going to building the strategy, how we are going to find the optimal strategy, right? The very first we'll use MST. We'll build the minimum spanning tree, right? The concept of MST, so that we can find the cheapest way to connect all the nodes, right? It is the way minimum spanning tree, the name suggests, right? Cheapest way to connect all the nodes. Then once we will build the MST, minimum spanning tree, then what we need to do, from this MST we'll remove what? K minus 1 most you can say expensive edges. Can we say that? Means very first we'll build the MST, then what we will do, we'll find k minus 1 most expensive edges and we'll remove it, we'll remove from them. So for this step what we need to do, we'll split this MST. What we will do, a split MST, right, into how many component, into k component. Can we say that? Then what we need to do, we have to find the maximum weight, max weight we will find, and max weight will find in the resulting k component, and that will be our answer. Understand? Let's understand the example. So if you understand the MST, right, let's suppose we can write here MST. Let's suppose MST will include 3 lighter edges. Can we say that? So if we will take 1 and 3 here, I'm taking the lighter edges, right? So what we have the weight here, let's suppose 1 and 3, weight we have is 2, correct? Then we have 1 and 2, you can consider from here, okay? So another will take 1 and 2, 1 and 2 weight we have is 3. These are the weights, and this is U and V nodes, correct? Now next we can say take 0 and 1 itself. 0 and 1, can we take? Yes. Give me once again. 0 and 1. So what is the weight we have here? 4, correct? So we exclude 3, 4 this time, because we have the highest weight is 6. So what we will do, we'll say 3, 4, we will having the weight 6, right? So this one we will what we'll do, we'll exclude this, we'll not taking this one, right? Because it's not needed for the MST, because its weight is highest, and so we'll discard it. And so let's break it from here, okay? So the remaining MST become what is 2, 3 and 4, right? The edges for the MST edges are MST edges are 2, 3 and 4. Can we say that? Now we let's suppose now we have k equal to 2. So we can remove one edge from the MST, right? We can remove from one edge from the MST. So remove the largest one. Which one we will remove? This 4 we can remove, right? Means this part we will remove. Can we say that? This 4 we will remove it from here, okay? So what we can say, when k is equal to 2 and we can remove how many edges? We can remove one edges. Remove one edge from the MST. So now after removing that, so first of all, let's suppose remove what? Largest edge equal to 4. And so the MST will become in 2 parts. First component will be 2 component will be, right? 2 component become, okay? So the very first component after removing this become what? Is 2 and 3, and its maximum cost is 3, right? Because it is 3. Other component is what? That just have one node, let's suppose, right? So other components will take we'll just say other components, right? And other components having only one node. So there is no edge. There is no edge means cost is 0. Can we say that? Yes, as per the if no edge is there, cost is 0. So we'll say that. But that's not optimal, right? Let's try something else. So give me 1 second, guys. Okay, so let's suppose, what is the something else we will try, right? Let's suppose, what if we keep edge 4? This time we are not removing this, right? And we'll remove this 3. Let's remove this, not this one, okay? It means we'll keep it this one and we'll remove this time 3, right? So 2 and 4 we have, right? The very first edge is or component will become 2 and 4, and this contains the max cost is this time is 4. Now we have component another one that contains 3, right? There is one edge is 3, so it is also itself is a 3, right? And so the cost is become what? For this time is 3. So it will become 3. But still, what we have maximum cost? Maximum cost is 4. So here answer will become 4. So among all the options that we will try either this or this, you will see that the minimum possible values for the maximum component cost coming is 4. That is we have here. And so we'll consider this example that this is having maximum value. Okay. So if you'll come here, you will see that remove the edge between node 3 and 4 and weight is 6, right? So you will just keep it outside and the resulting component has cost 0 and 4, right? So it is cost is whatever cost we have is 0. But if you take off all of these, right, 2, 3 and 4, right? So this time we are keeping this one and we are discarding this one, right? So we'll get what? Let's suppose we are discarding this one, right? This time. So what will happen? 4 we have is a maximum one, and this we have is we are removing this one, so we have 3. Between 4 and 3, which is the maximum? 4 is maximum, and here is 0. That is why it's saying that overall cost is 4. I hope you understand, right? Let's understand how to implement it. Okay, give 1 second. So very first, what we need to do, first of all, come here. Okay, the steps we have to follow is, let me zoom it little bit. Okay, the very first step is to sort the edges by their weight, right? So we'll sort it, right? And we'll say array dot sort will pass edges a and b, and it will become what? Integer dot compare a of 2 and b of 2. So the first is see, u is at 0, v is at 1, and the weight is at 2. So we'll take, let's suppose 2 edges we are taking, a and b. So we'll compare these 2 edges, and which one is a minimum? It will go up, and down one is coming max one, right? So we'll say ascending order. So you have to take like this, we have to compare like this. Okay, so we'll come ascending order here. Understand? Now we have to build the MST, and to build that we need the union find data structure, right? I hope you understand DSQ, right? So we'll use union find data structure here, disjoint union set, right? DSU. So for that you will create a static class that will contain the parent, and the parent having a rank. Also we'll create a parent array, and the rank will be there. You know how to create the union find. You will create a union find of this what called constructor. So we'll pass number of edges, number of nodes will pass. So you can find, you can write the all the nodes, right? All the nodes will contain, give me 1 second, I'll teach you. So what will happen? Very first we'll create a parent, right? A array, and its size will be the same. We will initialize through the constructor. Let's suppose n we have is 5. So let's suppose we'll start from here. Let's call 0. As you can see here, we are starting from 0, 1, 2, 3 and 4, right? So I means this is the node. This is nothing but node. We are talking about node 0. Node 0, what is the parent of the node 0, right? Node 0 parent is itself, right? So we can say node at I, parent at I means at 0. What is the value will take? As a 0 will itself will take. Okay, so we will initialize like this. What we'll do, parent make, we will make the parent of itself and will keep updating itself, right? Let's suppose we'll 0 has parent is 0. Now we'll take one parent is, what we'll take here, we'll take 1, 2, 3 and 4. Like this we will update initially. This is for initial. We'll find, you will take a union find data structure and you will create the parent, and parent you will initialize like this, right? And we will take the rank. Similarly all the rank will be, by default it will become 0. We will not have anything, so this is your rank, right? Like this you will find. Now when will the method will find anyone, right? So we'll check if the parent is not existing. If parent at x is not equal to x, it will pass any value, right? And then we will check the value of the node if it is not there in the parent, right? What we will check, what we will do here, if it is not equal to, we'll use the find method. this method itself, right? So you will get some value. If it is not going the else condition, you will call the find, right? Let's suppose for this node, right, we are going to find the its parents. Let's suppose this is not the parent. Let's suppose what will happen, it will go to find the another this one, so it will go to check another one. Like this we'll keep checking, let's suppose, just for example. Okay, I hope you understand. So that is why I'm not going in deep. So now what we need to do, once we will create the find one, then you will have to create that union method, where you will pass two nodes value x and y. So it will merge the node and it will create a new component. Okay, so for that you will find the rank of x and y using the find method, right? You will find the using the find method as we have already created here. So it will return you the parent objects, right? Parent node it will return. We will check if the parents of both meets equal to, we'll say false. It is false. We cannot merge it because this is in the same group. If it is less than, we'll merge it like this. There is a condition. This condition will match and it will merge it. Okay, I hope you understand these things. So we will first, what we will do here, we'll merge, we'll do the BST, and through the BST we'll create a number of node will pass, and we will create the graph, you can say, using the union find. Then we'll have a list of integer we'll take, and we'll say this is the MST weights, right? We'll iterate through the array, and one by one we will get u, v, and w. You will get from 0, 1, and 2. Now we'll merge it through u and v. So we'll keep merging u and v. Now you will get the weight, right? Once you will merge it, you will have some weight here, right? That we will add into the MST. So all the weight will add onto the MST weights. Now we'll remove k-1 largest edges from the MST. So for that you will do collection.sort and will pass in the reverse order, right? So once you will have this sorted one, right, you can say in the reverse order, then all the MST weight will be in the reverse order, right? Means we will remove, we want to remove the k-1 largest is, right? Because once we have all the weight in one place, mean in the list, once we will reverse it, we will know that at index 0 is a largest one. And so we'll create a for loop, and what we will do, we'll keep removing the you can say weight, the largest one, so that how many times will this loop go? Until k, right? k-1 means maximum 2 times we have. Let's k equal to 2, will maximum 2 times it will run from 0 and 1, right? We'll start from 0 and we'll go to the k-1. Okay, once you have or we will remove k-1, then what we need to do, we will check if it is empty, return 0. Otherwise find the max weight. Where is the max weight removing? MST weight. Give me 1 second. So what I'm trying to say, let's suppose we have the weights are there, right? Let's suppose this is MST weight. MST weight. So MST weight, first of all, after reversing, we are doing what? Reverse order. So we'll say 6, 4, 3, 2, and 1. Let's suppose like this we have. So this, let's suppose k equal to 2. So maximum 2 times we have to go, right? Very first we'll check k is equal to what? 0. Sorry, I equal to 0, means this loop will go 0 and 1, correct? So at 0 we'll see that this is 6, so we'll remove from here, right? Now once you remove this one, right, we'll go k-1 time, right? k-I should be less than k-1, means this I should go not only sorry, it will go until k-1, means till 1, right? Okay, so only I will go until 0, right? Until 0. So we'll remove this one. So remaining will become what? Is 4, 3, 2, and 1. Let's suppose. Just for example, I'm saying. Now, who is on the top? This is on the top. So this loop is completed, and you have removed this one from here. Now you will check, is it empty? No, this will not go there. Then what is on the top? 4 is on the top. So we'll get 4 in the top. Okay. I hope you understand. If you still have any doubt, please let me know in the comment box, and I'll request you to write the time complexity and space complexity into the comment box, so that I will understand that you understood the problem. If any doubt you have, please put me in the comment box, and treat that as a support, right? And for that you need to just hit the comment box. You also write to some comment if you want, but keep liking the video so you will get more videos like this. And thank you guys, thank you for watching this video, and keep subscribing the Expert Funda.